Alright, so my name is Gary, and today I'm going to talk to you guys a little bit about ion propulsion. So despite being one of the most effective means of traversing outer space, ion drives are actually a fairly simple device. But to really appreciate just how remarkable they are, I want to go over two things, and that's orbital mechanics and liquid fuel engines. And using that context, I'm going to go over what makes ion drives different and special. So as far as orbital mechanics go, I'm sure we all know that if you thrust an object upward, get out of the atmosphere, turn horizontal, and gain enough speed such that you never fall back down, you will have achieved an orbit, essentially. And that's governed by a basic equation we all learned in Physics 1, the centripetal force equation. And a modified version of that equation is up there. It tells you the velocity you would need in order to remain in orbit based on the universal gravitational constant, the mass of the object, and the radius at which you're orbiting. So say you want to raise the altitude of an orbit. That's what this diagram right here shows. So imagine you have a vessel in a very low orbit, right there, this circle right here, and you want to raise the altitude. So you pick a point and you thrust in order to gain speed. That change in speed is called delta V. So after you do that, you have an elliptical orbit with x eccentricity, and then at the highest altitude, you do the same thing. You gain speed. And then once you've done that, you'll have a circular orbit with the same altitude. So based on that maneuver, I have a question for you guys. Which orbit, the smaller one or the larger one, has a higher velocity? The smaller one. As you can see, the velocity scales inversely with the radius of the orbit. So if we spent fuel to gain speed, and then we spent fuel to gain speed again, how is that possible? On the elliptical leg of our eccentric orbit, we're gaining considerable potential energy. So our kinetic energy is being converted into potential, and that amount is so much higher than the kinetic we gain from thrusting. So the point of this is just to let you guys know that the meat of all navigational calculations in space flight is this variable, basically. Delta V is the most important thing you need to consider when you're trying to navigate outer space. So are there any questions about orbital mechanics at the moment? No? All right. Now, a very brief overview of rocket engines, liquid fuel engines to be specific. So those are fueled by combustion. Say you have a liquid fuel, kerosene, for example. The basic physics or chemistry of this would be you inject that fuel, combine it with oxidizer, because combustion can't take place without oxygen. If you didn't have oxidizer, it would be fairly useless in outer space. And then you allow those reactants to gain heat and expand very quickly, and they shoot out of the nozzle at a very high speed. Now, it took NASA a long time to develop a very useful rocket engine. They're not simple by any means, but the main thing I want you guys to take away from this is the reactants of liquid fuel engines exit the nozzle at approximately 1 kilometer per second. So now to describe ion engines and what makes them special. So ion drives use a gas, for example, xenon. You take xenon. You then expose that gas to a very hot wire through which a very high current is being run, and then that temperature generates a charged plasma. And since the plasma is charged, you can use supermagnets to accelerate the charged particles or the charged plasma at very, very high speeds, 50 kilometers per second to be specific. So that's 50 times higher a speed than the reactants of a liquid fuel engine. So that means you can get a lot more bang for your buck, essentially, a much higher specific impulse. Now, the pros of this is that you can get a lot of delta V using a very small mass of fuel, which makes your effective efficiency higher. But the drawback is that you cannot burn fuel very quickly. With a liquid fuel engine, you can just dump a bunch of fuel in, dump a bunch of oxidizer in, and it'll exit very fast. But with charged plasma, you have to heat it up, and if you have too much being dumped in there, you either won't be able to heat it up, or it'll break components, simply because there's such a high acceleration associated with these charged plasma. So are there any questions about ion drives at the moment? No? All right. Now, the culmination of this technology is currently taking place at this very moment. NASA is attempting to develop an ion engine, specifically a Hall thruster, and they're going to call it X3. Now, the differences that this engine is going to have over the other ion engines is it's going to have 3 channels through which the xenon is excreted. as opposed to 1 in traditional ion engines. It's also going to have a much higher power output so that you can accelerate your craft much more quickly. And to do that, they're going to need basically a complete overhaul of many of the major components. You're going to need to have more energy input. You're going to need to have stronger magnets. And basically, the reason they're attempting to do this is because if we're going to take humans to Mars, we need a better, basically a better means of traversing the solar system itself. So this technology essentially has the efficiency to make that happen. And there's a certain velocity, a maximum velocity, an upper bound, if you would, associated with different means of thrust. And the liquid fuel engines can only get you to about 40,000 miles per hour. Well, this engine should be able to get us up to 500,000, which is really groundbreaking. So that's basically all I have to say about ion engines at the moment. Are there any questions about the technology?
How would you start?
You would have to basically do the exact same thing, but in reverse.
Yeah, I guess let's end it here. It's
Okay.
6 minutes.